All right, so once you figure out what your limiting reactant is, and it might be lead nitrate, it might be potassium iodide, then you can figure out your theoretical yield. I want to show you how to set it up if your theoretical yield is lead nitrate. Okay, so if your theoretical yield, if your limiting reactant is lead nitrate, then you're going to start with the measured amount, the amount you actually started with in the lab of lead nitrate. Not the calculated amount. Are you listening? Not the amount you calculated when you calculated or did the mass-to-mass calculation for your limiting reactant, but the amount you actually started with in the lab. The white crystal you measured out when you started the lab. Okay? And we're going to put every starting amount we do over 1, the number 1, not grams, not moles, not milliliters, the number 1. Okay? Then we have to have a molar mass conversion unit to convert from this grams of lead nitrate to moles of lead nitrate. And we did the molar mass calculation already yesterday. I hope you have it written down. So if you will find your calculations from yesterday for the molar mass of lead nitrate, you can write the conversion unit. And please do that now. Give you a chance to practice. Find your molar mass calculation that you wrote in your notes yesterday. If you haven't done this, you need to be taking notes. If you haven't done this, you're not preparing for the test on Friday. Okay? You should have the molar mass already done and be able to write this out. Okay? Now, if you're grading somebody's paper, then you need to just be able to look at this to see if they have it right. Okay? Look at your notes to make sure it's right. If they have it on their paper, look at their notes and make sure they have it right. Yes?
Are you going to do potassium and iodine?
I have. Well, yeah. Yeah, I said I would. Okay. All right. So you calculated the molar mass of lead nitrate yesterday. Okay? You should have that. Visually reference that. Make sure you've got the right numbers there. Okay? I want to put down the numbers. Make sure you had the right numbers so that you can see if you're doing this right or not. Because if you don't have the right numbers, you still not going to calculate your limiting reactant right. Okay? You should have gotten, and if you didn't get this, you need to do your math over again, 331.2 grams of lead to nitrate. And that goes on the bottom here because the mass unit matches here, the species matches. What you want is the same units and species on the bottom here as you have on the top here. Okay? And on the other part of this fraction, this conversion unit, we want the other side of this equality statement. We've got this side with the mass. We want this side with the moles. Whenever you do a molar mass calculation, you always end with this equality statement in this class. Okay? Where you have the mass, the sum of all the atomic masses of all the elements in the formula, added up in units of grams, and then you set that equal to the moles of that same species. And so the other side of the equality statement goes on the top, and that's where we get a conversion unit. These two things are equal. Top and bottom numbers are equal to each other, and that's what's going to make it equal to 1, and that's why we can call it a conversion unit. A unit means 1. Okay? All right, so we can cancel units, cancel the species, and now we're ready to write a molar ratio. Well, in this case, yesterday, we wrote a molar ratio for going from one reactant, Ki in this case is on the bottom, and lead nitrate's on the top here, one reactant to the other. These two things on the left are the reactants. But today, if you're trying to find a theoretical yield, the yield is on the right-hand side of the arrow. And so what we're going to look for is the thing we collected over here. Okay? So instead of a molar ratio that starts with a reactant and goes to another reactant, we're going to start with the limiting reactant and go to the product we're seeking, which in this case is the solid lead to iodide. So let's see. The balanced equation is right here. I'm going to put 1 mole of lead to nitrate. There's an implied 1 right here, and we can use that as either 1 formula unit or 1 mole of lead to nitrate. In this case, we're going to say it's 1 mole. Okay, and then on the top we're going to put the thing we are seeking. Okay, on the molar ratio, you always put on the top the species you are seeking. In this case, we're seeking the solid that you collected. And when you figure out all the physical states using your solubility rules, this is the only solid. So that's what you collected. So we want to put lead 2 iodide on the top, and there's only 1 mole of lead 2 iodide. So that's what we're going to put here, 1 mole of PbI2. Okay. Notice I have the same units and species on the top of this fraction and the bottom of this one. That allows me to cancel these units. It allows me to cancel the species. Okay? Don't you think you should be writing this down since you didn't do this work, Tevin? All right. Now that we have moles of lead 2 iodide, we are ready to calculate the mass of lead 2 iodide, but not until we calculate the molar mass itself. I do know that I have to have the same units and species on the bottom here. I could go ahead and put that down there because I know I've got to have moles of PbI2 down here because that's the way we do our conversions. But I have to calculate the molar mass of lead iodide, and I haven't done that. Perhaps you already have. Well, I've done it in other classes, but I haven't done it in this class.
You did lead iodide because it was solid?
Yeah. When you did your lab, you filtered the solid out of a liquid, correct? You know what you did in the lab? We put you put everything you produced in the reaction through that filter with a vacuum, and you got a bunch of solid collected on a filter paper, right? Okay. Well, the only solid here is the lead 2 iodide, right? So that's what you collected. Okay. All right. So we have to calculate then the molar mass of lead 2 iodide. So lead is the atomic mass of lead. You'll find out on the periodic table is 207. Actually, it's the average atomic mass, 207.2, and the atomic mass of iodine is 126.904. Let's see, where's my make sure I write that down. 90447. Okay. In the formula, just the formula for lead 2 iodide, we have 1 lead and 2 iodines. So we're going to multiply the mass of the lead by 1. That should be Pb, not just P.
Where do you find those numbers?
From the balanced formula.
No,
Oh, are you talking about these numbers right here, the big numbers? Yeah, they're the average atomic masses. So lead is 207.2, and that's the number we have here. The definition of molar mass is it's the sum of all the atomic masses of all the atoms in a formula. So we're adding up all those sums. I'm sorry, not adding up all those sums. We're adding up all those atomic masses. And so we have 207.2, and here we're multiplying this by 2 because we have 2 of them. And it's 253.80894. 80894. We have 3 empty slots here. Since we're adding now, or about to add now, actually 4 empty slots, don't we? Since we're about to add now, we have to keep up with the empty slots to the right so that we can round off properly. Significant digits are important. So we're going to add this number to the 207.2. Oh, that's not right. 207.2. And we get 461.00894. Okay, but all of these numbers from here over are insignificant. We underline them, draw an arrow to show the rounded off answer. And so we've got 461.0 grams of lead 2 iodide, and we're going to set that equal to 1 mole of lead 2 iodide. And we're going to put those numbers, use those numbers in this equality statement, in this fraction to build a conversion unit. So the 1 mole goes in the bottom, the mass goes on the top, 61.0 grams of lead-2 iodide. Alright, we've got units and species to cancel here, and we're ready to do the math. Okay?
Why did I rate it off?
Because I don't have your number that goes here. Okay? Your number would go here. If this is your limiting reactant, your number goes here. Okay? Now, if your limiting reactant, if you calculated it properly and determined it properly, is potassium iodide, you're going to start with potassium iodide. And so you will put your measured amount of potassium iodide. And it goes over 1. Okay, we've got to have the molar mass here. You should have, yes?
Like, okay, you have like CD, nitrate, and nitrate I. Like, if whatever you start with, would you have the same reaction? If you have the same amount.
Oh, if they were exactly the same? Okay.
No, like, okay.
All right, so I think I understand your question. Let me see if I understand it by answering it this way, okay? If you start with your amount of lead nitrate and calculate your theoretical yield, and the mass you end up with at the end of that problem is exactly the same amount as the given amount of potassium iodide. Is that the question you're asking?
Like, if you work it out for both and you get like a number, like, would it be the same when it is reacting?
Yeah, it doesn't matter which one you start with. If you do it properly, you will conclude that the limiting reactant is the same regardless of the way which one of the two reactants you start your calculation with. Okay? What you'll do is if you start with one, you'll actually find out, well, that's the limiting reactant. If you start with the other, you'll find out that's the other species is the excess reactant, which just means the other one's the limiting reactant. Okay? All right, so potassium iodide, we calculated its molar mass yesterday, and we have 166.0028 grams of potassium iodide, and we put 1 mole of potassium iodide here from the equality statement you were supposed to write. Cancel the units and species. Okay. Then you need a molar ratio. All right, so we're going to start with the 2 moles of potassium iodide. Okay, in this case, it's not 1 mole on the bottom because this is the molar ratio, and the molar ratio comes from the balanced equation, and the coefficient in front of potassium is 2. So we're going to put 2 moles of potassium iodide on the bottom. We're still going to have that 1 mole of potassium or lead-2 iodide because there's a coefficient 1 here, or implied coefficient 1 here. So it still is 1 mole lead-2 iodide here. Okay, we want to cancel the units and the species, and we need a molar mass to convert from moles of lead-2 iodide to the mass of lead-2 iodide. We already have that. It's the same. Okay, and we cancel the units and species. So if your limiting reactant is potassium iodide, you'd set up your theoretical yield calculation like this. Okay? And the amount, once you round properly over here, at the end of the problem, that is the theoretical yield. Okay? That's the theoretical yield.